Thanks for the invite to come and talk to you all today. I'm going to talk about the role of artificial intelligence in geophysics. I just want to preface that I am not an expert in artificial intelligence or data science by any means, and don't let the sleeves fool you. I'm not a magician or a witch. I'm actually a geophysicist. I know that some people would say they're the same, but I'd hope that I can change that today. So a little brief overview of my relatively short career to those in the room today with lots of, probably collectively hundreds of years experience over me. Yeah, I went to the University of Melbourne and Bachelor of Earth Science and did my Master's majoring in Geophysics and worked in the field for a year. I published my work in 2022 and started the Exploration grad program with Newcrest, and recently, obviously, Newcrest doesn't exist anymore. We're now Newmont. So in the 4 years that I've been a geophysicist, there's been a real, uproar in artificial intelligence, which has taken the world by storm. And I'm sure all of you have interacted willingly or unwillingly with artificial intelligence in one way or another. And we're all quite aware of, everyone's talking about artificial intelligence, and there's this big new craze. And, I just want to talk a little bit about why that might be, and obviously delve a little bit into how that can help us with geophysics. So, start of 2020, we all know COVID also took the world by storm in January of 2020, and then a few short months later, in June of 2020, ChatGPT-3 came out and available to the public to interact with. And then just recently last year, we had ChatGPT-4, which dropped. And I just wanted to highlight here that each of the models of GPT that have come out have dwarfed the predecessor model in terms of the training parameters and amount of data that has been used to train these models. And I hope some of you remember Clippy, and just want to point out it's an exponential growth here that each model has been trained on in terms of data and parameters. And yeah, this might be one of the reasons why AI has really taken the world by storm, is because ChatGPT is so accessible and everyone can interact with it, and it's on a global scale. It's not, it's not that if you can't afford it, you can't interact with it. It's, it's available to everyone. So, and yeah, I just want to point out that, so the last iteration was trained on 1.76 trillion parameters. That's not confirmed. It's based on some research that's been done on the performance of the model. And before when I made this slide, it hadn't been announced yet, but since then it has been announced that GPT-5 will be coming out, and it will also dwarf its predecessor in terms of the amount of data and parameters that it's going to be trained on. So yeah, it's really crazy and unfathomable numbers here that we're talking about in terms of the data that it takes to train these models. But I do want to point out that artificial intelligence is not a new thing. Even though we're all talking about it, and the craze of the time in the last 4 years, it's really picked up. It's not a new thing. Machine learning's been around for over 70 years. The start of statistical methods were discovered before 1950s, and there have been ebbs and flows in terms of the money and the research that have gone into developing these tools, and there has been AI winters and things like that. But really, in the last 5 years, 4 to 5 years, generative AI has led to groundbreaking models in AI and really central to the public, which is why we're all talking about it. So what is artificial intelligence and machine learning, and all of these things are really hard and complex to wrap your head around sometimes. And all machine learning is AI, but not all AI is machine learning, and that can be hard to think about. But and there are sort of infinite categories and subcategories and tools that come under these, and combinations of supervised and unsupervised and reinforcement learning, and a lot of these words that you'll hear thrown around when talking to colleagues or other clients or the like. And yeah, I just want to point out that, like I said before, these things are all around us. Things like your facial recognition when you open your phone, the algorithms that set your Netflix and Spotify recommendations, your self-driving cars. All of these things use artificial intelligence, and they're well integrated with our daily lives and have been for a number of years. It's like I said, it's not a new concept or a new thing. So yeah, why the big boom all of a sudden? And I think maybe we can contribute some of that to the compute power that we now have available to us and the cost of actually running things on those supercomputers. This graph is a little bit hard to look at. There's sort of two axes on here. And the first one I'll talk about, which shows the top 500 supercomputers in the world and the performance of those supercomputers in terms of flops, which is a floating point per second operation, which should be FPOPs, but it didn't sound as cool, so they called it flops, which has also shown exponential growth. And this is just from the 90s. And the last sort of iterations of supercomputers that have come out are now exceeding 1 exaflop, which is just an insane number to think about. It's got 18 zeros after it. And I just want to, for a comparison, say that the other axis on this graph is showing you the cost per flop in USD. And if we were to imagine that supercomputers never, or computers in general, didn't develop or evolve past what they could achieve in the 1950s and 1940s, to run an inversion, let's say, on that computer in today's money would cost far over $10 quadrillion, which has 13 zeros. So just think about the scale of performance that our computers are able to achieve today. And that this graph is upward trending still. It hasn't tapered off. It's still going to continue to increase, and we're going to have access to more and more compute power with time. And also just to point out that the cost has decreased over that time almost at the same rate. So now we're looking at something like below 10 cents per floating point operation per second. So maybe in today's money, it might cost you, I don't know, $2,000 to run an inversion that runs for 2 weeks or something like that. There's some loose numbers. So maybe this is contributing to, why the big uptake and craze around AI, and it's going hand in hand with the development and the research and the funding that's going into not just making our computers better and faster, but then those tools, those AI and machine learning tools, are then able to be pushed and tested and developed even further. And just an interesting aside note that out of those top 500 supercomputers in the world, the US has over 50% of those, and Australia doesn't even make the top 10. We have 5 of the top 500 supercomputers in the world, and I just want to point out that at least that we do have access to this compute power here, and we can develop things and tools, and yeah, we can do that in Australia. Okay, but Mikayla, you haven't even talked about AI and geophysics yet. You've just been talking about AI. So I'll start off by saying that, like AI has been around for over 70 years, we have been using some of these tools in geophysics already, and more recently, with the development of deep learning, there are some really great research studies out there, and this is just a table that is showing some of those papers from the last 5 years, and you can see some of those names are repeated. And so there's not a lot of people doing the research in this space, but there is research being done out there, really good stuff. And I'll go into a few examples of some of those tools and some of the ways that we're already using artificial intelligence in geophysics. So these are some of my kind of favorite applications that are quite recent. These are all from the last 5 years or so. First one here is 3D inversion clustering. So this is combining your statistic deterministic inversion, like problem solving, with 3D clustering and predictability. So say you have 2 or more geophysics surveys that you want to invert for your petrophysics properties. You can now cluster that in 3D to have a semi-automated geology differentiation, and this is really important for the greenfield space because we're in areas where we have really sparse data points and drill hole locations. So if we can better predict what's happening between those points whether we have measured data, then obviously that's going to increase efficiency and in time and money into generating our exploration targets. Another example here is ergodic sampling, which is a method of reconstructing data from a set of samples that could be as low as 10% of what you would normally need to acquire a geophysics data set. And the 3 examples here show a random, ergodic, and full sample data set, and the reconstructed images from those data sets. And ergodic sampling has demonstrated that the reconstructed image from that is, you could say that you'd probably your targeting strategy might not change too much between the fully acquired data set and your ergodic sampled data set. And I mean, this is groundbreaking for greenfields exploration as well, because if you don't have to, if you can acquire just 10% of the data that you would normally, obviously, then that's up to a 90% saving cost in time and money, which is, you know, what we're all about. So another example was probably more obvious to most is seismic data. And there's always continual research into how we can make processing and image enhancement in seismic data cheaper, quicker, all of those things. And this is just one example of noise removal from a data set. And I think this also has a lot of value to add, because if you do have those historical data sets, you know, you've acquired a big seismic array 10 years ago, the processing on that data will be, you know, what we can do today on the supercomputer power that we have available to us is going to far exceed what was done 10 years ago or even 5 years ago. So being able to go back to these historic data sets and then reprocess and re-perform our image enhancement is going to add a lot of value, and we may see features in that data then that we couldn't before, and, you know, generate new targets. Another example that I thought I'd throw in, which was sort of current, was, you know, aurora prediction. So kilograms of aurora imagery have been fed into this model and classified, and then the model's been able to predict where and when you might have an aurora. We had one recently, and so, you know, this lets us know where and when we need to get out there with our cameras so we can take these amazing pictures of aurora around Perth. So this is one from last year. It's just a fun example of where we're using machine learning and artificial intelligence. Now I want to talk a little bit more about the seismic application. This paper is just dropped, I think, a month or two ago. This is really recent, March 2024, and it's boasting the integration of machine learning for high performance and cloud compute engines to further amplify computational capabilities, and boasting a reduction in turnaround time of up to 70%. So, you know, there are clear advantages in doing research into making our processes more efficient. Now, this leads me into one of the first issues that we face as geophysicists with integrating AI tools, and it's the data problem. One example I just wanted to touch on is one SegWi file of a 2D seismic array of approximately 50 kilometers in length, reprocessed just last year. So it's, you know, it's fairly new processed data, sort of the latest kind of technology. The file size of that is 35 gig for just the one file. So if you remember back to the graph I showed with the GPT models coming out, and each model iteration is trained on exponentially more data and parameters. If we think about training a model, I'll just move to the next slide. We think about training a model on predicting a feature of interest, for example, like a salt dome in our seismic data that we might want to chase, you know, oil and gas. The amount of data required, and just the minimum amount of data required, is already jumping up to like big amounts of data, 35 gig per one image. Some of the image predictive or generative tools available today are trained, the data that they're trained on, those images might range between 1 and 2 meg. So that's the level of difference between the data size or the file size of the data that we're using to train. A lot of the papers, the research out there today, have, like, there's a bit of ambiguity, but most of them come down to the same recommendation, that you need 10 times as many training samples as you do features of interest. So at a minimum, we would need 10 examples of that salt dome labeled good quality data to be able to train our model on. And the more data you have to train your model, obviously the better the model is at predicting those things. So there is a fundamental flaw or data issue, if you like, with integrating AI into geophysics. But there is hope. Those supercomputers are still trending upwards, so they're only going to get better, and they're going to be able to process more. So maybe the data issue of the size of our files, maybe that'll go away with time as our supercomputers get better and better. But there's still that fundamental issue of data quality, and I'm really glad that Justine went before me, and I wish she went. But you know, data in, data out, and the quality of your data that you're feeding into models obviously going to dictate how good the quality of your outputs are. And that leads me to this next point, which I'll just also mention that not just data quality and the size or the amount of the data, but also data access. In Australia, we're very lucky that we have a lot of open source data sets. The government provides a lot of that for us. But if we look at global trends, normally geophysics data is quite siloed within companies that are acquiring this data, and they're all really protective over that data. So data access to be able to train your models on a wide variety of examples is also a limiting factor and an issue that we need to talk about. So I want to talk about inversion, because inversion is one of those tools that as geophysicists we use quite readily. And yes, it's based on more statistic and deterministic algorithms that have physics inbuilt and are quite supervised. But I would say that in thinking about inversion or talking about inversion, there's quite a lot of similarities when you think about AI tools because of the black box nature and the incomprehensible complexity in the math that goes into these things. And a lot of people that use these tools may not fully understand what's actually happening to the data when, you know, they feed the data in and they click the button and they have the outputs, may not understand how that was actually manipulated in the process. And so I think that there are some parallels that we can draw between these two tools. And I just want to highlight that that's what I think AI is. It's another tool that we can use. And the other point that I want to talk about here is the ambiguity, the inherent ambiguity in geology in general. You know, as explorationists, we do try to tend to put our deposits into boxes: orogenic gold, epithermal gold, IOCGs, so on and so forth. But really, no two deposits can ever be exactly the same, just by the nature of the complexity of the Earth and how dynamic it is. So it's really hard to train models on like data when every bit of data is slightly different. I've got two examples here of some of the list of parameters that you can change to manipulate the outcomes of, say, ChatGPT compared to a potential field inversion. And I'm going to talk about one of those, which is the beta, and just to highlight how easy it is to misuse a tool such as inversion, which has been around for a while, which we use readily, which is grounded in physics-based and all those things. But it's really easy to misuse these tools. And this is three examples of three stages in an iteration that you might, in an inversion that you might run. At iteration 3, the data is being loosely fit, but the misfit hasn't been achieved yet, so there's still room to manipulate that data. In iteration 6, we've achieved our misfit, so the difference between our observed data and our predicted model is acceptable. It's within the error that we've said is acceptable. And then we see at iteration 15, the difference between the observed and the predicted is almost perfect. It's, you know, it's great. But then we look at the model and it's just rubbish. Like, it's not geological at all. And I think this just highlights that, you know, misusing inversions could be as simple as using the last iteration and not knowing how to interrogate your outcomes. And I think the same can be said about using AI tools. If we don't know how to interrogate the outcomes of using these tools, that's where we fall into the danger of, you know, making a recommendation to our boss or to our client or whatever that might be, to go and target off a model when you don't really know what that model means. So there are a few challenges, and I only spoke about sort of the data side of things, but here are a few of the other challenges that we're going to face and that we already are facing. And I just wanted to talk about AI hallucinations. I don't know if any of you have heard about this, but one of the inherent parts of making an AI model sound more human is introducing source reference divergence, or essentially a component of pseudo what's the word? Anyway, you kind of like white lies. Like, we tell white lies as humans, and that's a part of natural language, right? So they have to build this into the models for ChatGPT, for example. And this is a real example of a data scientist wanting to test this, and she asked the bot to tell her about cycloidal inverted electromagnon. And the bot replied and said, yep, I can tell you about that. Here's a list of scientific academic papers that have been published and all the evidence you need to research this. And it's a completely made up thing. And she knew that, so she was trying to trick it. And it's just an example of how we can't guarantee these new generative models that are coming out today. We can't guarantee any truth in the outcomes. And so that's one of the other challenges that we're going to face in trying to incorporate deep learning tools into geophysics, because geophysics is fundamentally a grounded and truth-based problem that we try to make it as grounded and truth-based as possible. So that may be something else we need to consider. Other issues, obviously, or maybe not so obviously, are around bias, which Justin also touched on, in how easy it is to have bias in your data or introduce bias in your data. And then if you feed that or train your model on that data, you're going to have biased outcomes. Security risks, the complexity of geology and the inherent nature of the ambiguity, the data availability and the quality of the data, the black box nature of using artificial intelligence. And there's a lot of misconceptions, so I think education is one of those things that we really need to consider, and we need to keep talking about these things. Overfit and generalization. Compute power obviously is one of those things that is a limiting factor, but as I said, there's hope there, because that's an upward trending thing, and that's just going to keep developing and keep getting better. Accountability and liability is an interesting one, and I was talking to some people here before the convention about this, and how there's not really any legislation yet, or they're trying to start develop these things. But if I use an AI tool to predict prospectivity analysis in a greenfields area using geophysics, and then I say, yep, I'm going to go with this model, this outcome, let's go target this one, put a drill hole here, and they come up with nothing. Who's accountable for that? Am I accountable? And is it the model? Is it what? Yeah, there's a little bit of uncertainty in that area still. And obviously the ethical use and how using these tools may impact people, environment. Compute power is great, but it actually costs us environmentally to run things. And I think that is it's an unseen factor, because we don't really associate, like we would with mining, pumping things into the atmosphere and the detriment it might have on the environment. We don't really associate that with running an inversion on a computer, but we probably should think about those things more. So I'll finish on talking a little bit about the future of AI in geophysics, and I really think there is a lot of hope in using AI tools in geophysics, and I've put it, limit does not exist, but really there are limitations currently, and there is a lot we need to do to get to the point where we can readily use these tools that are in a constructive way. And I think where we can focus our energy today is to make sure that we have better input data, so making sure the data quality is up to standard, and we have labeled data sets that we can train models on, because currently that's a big challenge. I think that this siloing of data could probably be tackled by something like consortium-led initiatives where companies come together and pull their data together to train models on. I think that the more we have grounded large language models like ChatGPT, but in a grounded way, obviously reinforcement learning has started to manipulate how those models learn. I think we could use those to have tailored LLMs trained on organization documentation to continue education in geophysics, making knowledge graphs, and having a bot that essentially you could ask a question about geophysics. Maybe it's a theoretical question or something like that, but I think that could be a way that we could use this technology today in a positive and constructive way. And I think, the future is really exciting, and I think maybe the future will be in using generative models, but combining that with constrained, grounded physics incorporated inversions. And I think that would be a really exciting thing. And I think just keep talking about this, keep the conversations going, keep education up, and add the tool to your toolbox. And I think it's exciting, the future. That's it.